Hey guys, welcome back. It's day 8. It's Monday. It's a beautiful Monday. And by beautiful, I mean way too hot. Why does summer exist? Today we're going to be looking at simplifying radicals some more. We're going to be looking at how to simplify radicals involving variables. Many of you guys seem to do really well with this section. I was impressed. This is mainly because when I talk to my students about this is one that tends to be a big struggle. And so I'm super happy that you guys are doing well in this section so far. We're going to do 2 more days of stuff involving radicals. Today will involve radicals with variables, and tomorrow will involve radicals in the denominator again. Looking at special cases where you have to rationalize the denominator, which means that on Thursday, which is about the halfway point of on Wednesday, about the halfway point of our class, we will have our first quiz. So that'll be something to look forward to. Yeah, look forward to. There'll be no homework that day. There'll be no lesson that day. It will just be a quiz, and I will be posting a video going through questions similar to the quiz to kind of give people that need the extra help some extra heads up and remind ourselves of how to do the different problems. There'll be questions from each section, similar to the ones we've had in our homework, and I will try to choose ones that seem to be the most missed ones from the homework, that try to push those of you that are struggling to try and figure out what's going wrong and to get those things fixed. So let's look forward to that, and that'll be what's happening on Wednesday. Excuse me. For today, let's take a look at how to rationalize a radical that has a variable inside of it. So let's get started. The first example I want to look at is this one. The square root of 162, a to the 5th, b to the 4th. Let's first remind ourselves of a couple of things. First of all, there are exponent rules. We went through this list before, but let's go ahead and take a look at them again more in depth, shall we say. These rules include things like, anything to the 0 power is 1. If it doesn't have a power, we assume that power is 1. And it has a power of 1, we can make that power disappear. If they have the same base, and you are multiplying them, you may add the powers. If they have the same base, and you are dividing them, you may subtract the powers. If they have the same base, and they are inside a radical, I guess they don't need to say base, do they? A to the m to the n, you may multiply the powers. And then there are a few radical rules that are helpful to remember here as well. If you have the square root of a times b, you may rewrite it as square root of a times the square root of b. Same with the fraction, square root of a over b. A is equivalent to the square root of a over the square root of b. And then the one that's very particular is squares and square roots always cancel. And so with these 8 rules, we're going to solve every problem we have today and every problem in your homework. The detail is figuring out how to apply the different rules in different ways so we can make sure to get the solution we're supposed to get. So let's take a look at this problem, this first example. So because of this property right here, which states that if you have things being multiplied, you may separate them out. One of the things you can do in this particular problem is to rewrite it not as 1 radical, but as 3 radicals. All being multiplied together. And so that's an allowable step. It's not the only step you can take, but it's a decent step. Because now we can look at the first one, like we did last time, where we try to find the factors of 162, which would be 81 and 2. But we can also do now with this variable, because remember, you can rewrite a to the 5th from another property. A to the n power just means the number a written out m times. That's all it means. And so, for example, a to the 5th just means the letter A written out 5 times. B to the 4th just means the number b written out 4 times. Why is that helpful? Well, let's look at the first piece. We can split that apart again, so we can the square root of 81 and the square root of 2. But now we can pair these together and rewrite them using that rule again. So for example, this becomes a squared, and a. So I take these two, group them together, and put them in their own radical. These two, group them together, put them in their own radical. This one is by itself, I leave in its own radical. And the same thing here. So we have b squared and b squared. What this lets me do is to be able to take our function and take it from a complex function under one radical and split it into smaller, simpler radicals. For example, the square root of 81 is just 9. The square root of a squared is just a. The square root of a squared is just a. The square root of a is just the square root of a. The square root of b squared is b. The square root of b squared is b. Remember, all of these were multiplied together at the beginning, and all of these are multiplied together here at the end. Meaning I take this radical that I started with, and through a process transform it into this statement, which contains all smaller radicals. Now, from here, I should make sure to put it in the correct order. So 9 would go out front. The square root of 2 and the square root of a are going to move to the end. But let's look at everything in the front. I have 2 a's, which would make this a squared. Because remember, if I have 2 a's, it'd be a to the second power because they're being multiplied. I have 2 b's, which would make this b squared. And I have the square root of a and the square root of 2. And then I can merge those two square roots back together using this property again. So you can see how you end up using the same properties multiple times. But in the end, you know you've got a good answer if the following statements are true. The radical is at its smallest possible value for what's inside of it, or the radicand. So 2 cannot be square rooted. A cannot be square rooted. 2a cannot be square rooted. Therefore, this cannot be square rooted any farther. So this is the most simplified answer we can get. Now, this is showing a lot of work here. I do not expect this amount of work from you guys, because there are obviously a lot of shortcuts, but this is the process you go through when you look at a function like this. Let's look at another one. And second example. Most of our work today is going to be examples, because there's not a lot of new stuff. It's just reusing old material. So if you don't know these things well, I don't want to do new things until we get some extra practice on them. So let's look at this one. The square root of 150 x squared y cubed z. X squared. Make sure that's nice and clear. All right. So it's like before. One of the things we can do when we have a big radical is we can break it into a bunch of smaller radicals. As long as what's inside the radical is being multiplied, you may break it into separate radicals that are being multiplied. That's the big detail. The same operation exists here as here. What you cannot do, you cannot do this if there's something like addition. That doesn't work. There are numerous examples where you can try it and this just doesn't work. Don't do it. It has to be, you start with multiplication, you end with multiplication. You start with division, you end with division. You have to keep the same operation, and it only works for multiplication and division. So over here, let's split this apart. This becomes square root of 150, square root of x squared, square root of y cubed, square root of z. So now I can start splitting these things apart. The square root of 150, let's see, I don't know my 150 very well, so I can break it down into my little tree. 15 and 10 would be a good one. Now 15 breaks down into 3 and 5. 3 and 5 are my prime factors. 10 would be 2 and 5. Those are my prime factors. This becomes 3, 5, 2, 5, all multiplied. Times the square root of x squared. Now I'm going to leave this one. I'm not going to bother splitting it apart because it's a square root and a square. Like, I already know that's going to simplify using this property, so I don't bother rewriting it. But the y cubed is y times y times y, and the z is just a z. Now, just like before, I can group things together in order to make this a little nicer. So this becomes the square root of 5 squared. So I've moved the 5 squared on its own, which again I'm allowed to do, because again they're all being multiplied. And I move the 5 squared specifically because it's one that will cancel, and so I leave it by itself. The 3 I could split off, but I notice it's not going to cancel, so I don't bother. Same with the 2. It's also why I keep the x squared, just the x squared. I can split this y into y squared and y. So you'll notice that at this point, nothing has changed, right? I still have 2 x's, because I have x squared. I still have 1, 2, 3 y's. I still have 1 z. And if I took 5 squared times 3 times 2, I would get 150. So far, nothing has changed. I have the exact same function, just written out in all of its split up form using our rules. But the reason why we do this is to make this process simpler. The 5 squared will cancel with the square root, leaving the 5 behind. The 3 and the 2 don't cancel, but 3 times 2 is 6, so I can write it as a 6. The x squared and the square root are going to cancel, leaving an x. The y squared and the square root are going to cancel, leaving a y. The square root of y doesn't do anything. The square root of z doesn't do anything. Remember, the only way to get rid of a square root is by matching its power. So, I have these 7 pieces all multiplied together. From here, I can regroup. The 5, the x, and the y can go out front. The square root of 6, the square root of y, the square root of z can all be merged back together just using this step in reverse. So going from separate radicals to one radical, this becomes 6y z. There's the solution. So what we're doing here is we're taking our function, our problem, and we're finding ways to split it apart using our rules until it gets to a place where we can actually do some simplifying. Because this doesn't simplify. There's nothing I could square that gets me 162 a to the 5th b to the 4th nicely. And so it's better to rewrite it as all these different little pieces, cancel those pieces using a property, and then have our simplified version with the smallest possible radical. And again, down here, let's verify that fact. 5x and y, that's fine. But we have to check to see if the inside is correct. Well, 6 does not have a radical, and nothing goes into it that's a radical. Right? You can't put it into a 4 or a 9 or a 16 or 25. Like, it's just 6. Same with y, same with z. And so this is the smallest possible radical that is acceptable. Now, we can do this exact same thing using fractional powers. So let's take a look at this one. The square root of 2x squared over 9y to the 4th. 2x squared over 9y to the 4th. Okay, so this. So just like before, what I can do is I can take this fractional radical and break it into 2 separate pieces. So I can take the top piece and break it into one radical, 2x squared, and the bottom piece, make it a separate radical, 9y to the 4th. So that's using a property. From here, one of the things I can do is I can take each of these now top and bottom radicals and use this first property up here to split them into separate ones. So I can do square root of 2 times square root of x squared, square root of 9 over square root of y to the 4th. Now, at this point, I'm going to showcase one of the ways you can do this process a little bit faster. It's important to remember that there is a definition of a radical called a rational, where it means it is a to the 1/2 power. Why is that so helpful? Because there's another way to write the square root of y to the 4th. A be y to the 4th to the 1/2 power. Why is that so helpful? Well, because of this rule, rule number 5. we could take this y to the fourth to the 1/2 power, and it would become y to the fourth times 1/2, and 4 times 1/2 will be y squared. And so it allows us to take this step. Well, we know the square root of 9 is 3, but it allows us to go from the square root of y to the fourth to just y squared in one step, rather than having to write out all the components and then simplify. It's a nice little trick you can use in order to get to a faster solution. So, the square root of 2 is just the square root of 2. The square root of x squared, remember squares and squares should cancel, leaving just x. Excuse me. Square root of 9 is 3. Square root of y to the fourth, according to this property, would become y squared. And we can always verify this just by doing the process, right? The square root of y squared would be y times y times y times y, which would be the square root of y squared times y squared. We could then split it apart into square root of y squared times square root of y squared, which would become y times y, or y squared. And so we know it's going to work. It's just which one's faster. You know, it's easier to do this quick math in your head, where you take 1/2 times 4 to get 2, than it is to write out all these components. If you find you're getting the wrong solution, though, you may want to take your time to write it out like this process shows. Okay, now to get to our actual solution, we need to make sure to put everything in the correct place. So we have the square root of 2x. So remember, we put the non-radicals first, and the radicals second. And then 3 times y squared would just be 3y squared. There's our solution. Again, there's no new material today. It's just using old material, old material in different ways. Now, let's take a look at another one. And on this one, there's actually a different way to solve this. And so we're going to solve it once using kind of this technique, and then once using like other rules to make the process a little simpler. And it has to do with simplifying first. So let's keep those rules visible as best we can here. All right. Let's look at our next problem, our next example. This will be another one where we have a rational example where it's a fraction. Let's do the square root of 234 x to the 11th y over 26 x to the 7th y. Now, we could begin this process like this is option A. Option A says we split. We take this property and we take this fraction and we split it apart. What is that going to look like? Well, we're going to have the top one, 234 x to the 11th y, divided by the bottom one, 26 x to the 7th y, and then we continue like normal. However, in this example, this is harder than if you chose to do option B. Option B says simplify first. We know we have these rules that allow us to simplify fractions, specifically this rule number 4 here. And so what I can do is, instead of splitting it, I could start simplifying some stuff. There you go. So for example, I have x to the 11th on top and x to the 7th on bottom. That would make this x to the 4th. Remember, we subtract. 11 minus 7 would give us a power of 4. I have y over y. Remember, that would be y to the first over y to the first. This become y to the 0 power. We can even simplify the numbers. 234 divided by 26, we could take a 2 out of both of those. On bottom, we end up with 13. And on top, we end up with 234 divided by 2 would be 117. I believe that is correct. And I think that actually simplifies even farther. Because 13 goes into 17 9 times. And y to the 0 power is, of course, 1. So notice how we took this nasty fraction and instead of trying to simplify this thing, which if you simplify this, yes, you will eventually get down to the same answer, but it is a lot harder to do because the top piece is not a nice thing that simplifies. The x11 doesn't simplify nicely, the y doesn't simplify nicely, the 26 doesn't simplify nicely, the x7 doesn't simplify nicely, the y doesn't simplify nicely. Nothing in here simplifies nicely. But here, like, we got to this point and now we're at this point. This simplifies very nicely. We could split it apart, the square root of 9, the square root of x to the 4th, and then the 1 disappears because it's a 1. The square root of 9 is, of course, 3. And then using that same property we did with the y to the 4th, we can do it with the x to the 4th, turn this into x squared. By comparison, this will be much simpler and much faster. If I was to do the top one, like, let me see if I can showcase what it'll look like. I'm going to skip a couple of tiny steps just to kind of showcase how it works. But in the end, you end up with this. Now, from here, you can obviously see that, some stuff's going to cancel, right? X, y, and x, y on top and bottom should cancel. X to the 3rd, x to the 5th should cancel and become x squared on top. But then you have these radicals, and if you don't see it, they go together, then you're going to quickly have to try to figure that out. But eventually, you will end up with 3. Because when you try to rationalize this, it will end up fixing itself. It's just a pain. Like, this is a lot harder math to do compared to here. And so don't forget, simplifying is always an option and usually your best option. If you can simplify it right now, do it. If it can't be simplified right now, don't do it. Save yourself some headache. Let's look at one more before we go on. Okay, just like before, I have two options. I could, option A, immediately try to start simplifying the top and bottom separately. So break this thing apart into the square root of 9 times the square root of a to the 5th times the square root of b to the 14th. And then on the bottom, I could do square root of 3, square root of a to the 4th, square root of b to the 5th. Like, that's an option. But the better option is to actually recombine them. Because when you recombine them, they become much nicer fractions. 9 over 3 is 3. A to the 5th divided by a to the 4th would become just an a. Remember, subtract the powers. 5 minus 4 is 1. And anything to the first power is just itself. And then b to the 14th divided by b to the 5th, this would become b to the 9th. And this is much easier to simplify than all of these, right? Because you can clearly see that the 3 and the a aren't going to simplify. The b to the 9th will eventually become b to the 4th, 3ab. Like, it is just much easier and nicer to work with compared to this one. Because even if you do this first path, right, you get 3 on top, a to the 5th becomes a squared a, because you break the a to the 5th into a to the 4th times a, and then b to the 14th becomes b to the 7th. On bottom you have the square root of 3, you have a squared, you have b square root of b, and then now you got to simplify this nastiness. Like, this is not easy to do. You can cancel the a squared and the a squared, but these two don't interact because one's a number, one's a radical. The b can cancel with the b, but not the b on the inside. And so, like, it just becomes this nasty problem. that is almost impossible to deal with. And so it's much simpler and easier if you use a combination of rules to try to find a different path to get to your solution. I want to showcase one more example. I did not get enough time to talk about this last time, so I want to make sure to do it now. If you have operations in between them. So let's take a look. Our last example. 3 square root of 80x minus 4 square root of 45x. Okay. From here we can simplify. Let's do a piece at a time. 3 square root of 80 square root of x minus 4 square root of 45 square root of x. The 3 stays a 3. The square root of 80, I happen to know my multiplication tables really well. This is 16 and 5. 45 is 9 and 5. Now we can split it apart into 3 square root of 16 square root of 5 square root of x minus 4 square root of 9 square root of 5 square root of x. The square root of 16 is 4, so 3 times 4. The 5 and the x, neither one simplifies, so I can merge that into 5x. 4 times the square root of 9. Square root of 9 is 3, so that would be 4 times 3. Square root of 5. Square root of x. Oh, I could do the same thing over there. Which means this becomes 3 times 4 is 12. Square root of 5x. Minus 4 times 3 is 12. Square root of 5x. And from here, like, I could factor this to showcase how I get my solution, but I have the first term minus the same thing. Anything minus itself is always 0. And so that's a possibility. But notice these two are the same thing, they're just written in very different ways. Which is why simplifying is so important. Because if I write it this way, and you write it this way, we think we're talking about different things, but in fact we're talking about the exact same thing. The exact same thing. And that's pretty important. It happens more often than you think in non-math places, where people argue and fight over, well, I wrote it this way. Well, I wrote it this way. But in reality, they're the same thing. And so when you put them against each other, they end up canceling out. Okay. You have your homework assignment for tonight. It'll be posted along with this video. Please make sure you are ready for your quiz on Wednesday. We'll have no new material on Wednesday. Tomorrow we will look at how to rationalize its denominator. So we have a radical in the bottom. That'll be our last thing before our quiz, and our quiz will consist of the 4 topics we talked about so far. So make sure you are ready for that. Otherwise, hope you guys have a fantastic Monday, and I'll see you guys tomorrow.